first and then share the screen. Okay. Good. So first, let's go ahead and look at that our codes. Okay, the related to our homework first. Okay, we have plenty of time to then we can go through the theory behind that one, and then I can just go through those 3 slides, the PowerPoint slides that we have for chapter 1, 2, 3. And I have already uploaded all other slides as well for all other chapters too. If you go ahead and check on week 2, week 3, and week 4, you can see pretty much the whole book being condensed over there. Then that way, I don't think you have to necessarily buy the textbook or anything like that. Okay, but if you want, you can go ahead and buy that. It's a great book. I actually that I have talked to that the author personally. I have talked to him too. I know him personally too. But I didn't recommend that textbook. It's recommended by the that your university. Okay. So anyhow, let's go ahead and look at that little bit. Run this one more time, and then see how this gonna. We have any issues over here. This is related to that how we're gonna get the data. Okay. Let's get the data. We discussed yesterday several ways to get this done. So this is the data set, the cost data. It's a make, model, type, origin, drivetrain, MSRP, invoice. They were being given in dollars. Later on, since they were in strings, we're going to change that one to numerical format. Engine size, cylinder, horsepower, MPG city, MPG highway, weight, wheelbase, and length. So pretty much these two we're going to change into numerical the format or the quantitative format as we mentioned yesterday. Okay. So they were already there. These are the several ways of getting this data imported. Okay, if you want, you can go ahead and print too. Okay, so that similar to this one, that if you are using that R or Python, they were very powerful than this one, because R and Python you can do so many things than what we do on this one. Mainly on this one we do the graphical representation and all kind of stuff. But this is a powerful tool too. But R and Python and Julia, they are more powerful than SAS. But anyhow, the SAS is that language that the programming that we have to use over here. Okay. So later on, this is the several ways of getting this done. The same thing. See, if you're going to use the verb, I created the data out library. It's already over here. If you go to the library, see. Is within this library, data out has been created. Within that one, we can see that this data, cost data, has been renamed as a Sumit cost, and see, save over here. Okay. So then what we did was we changed, see, the format being changed, the dollar being converted into numerical through this process. See? And then we're gonna call them with the new labels, new variables, MSRP underscore 1000, invoice underscore 1000. And it's been added to that our data set again. See, if you go ahead and see, look at here, see, MSRP 1000, invoice 1000. See, no more. The dollar sign has been gone, and then in addition to that one, we still have that MSRP and invoice with the dollar sign and that comma. This here comma has been taken out. It has been kept to 3 decimal places. That means being divided by 1000. Okay, that being divided by 1000. This 3 means like how many decimal places to the right of that decimal point, and this is the whole by the width of that string. By default, here we have mentioned that yesterday. By default, 6, 2, and 32. Okay, range this one 0 to 31. Okay. And then what we did was that we just draw that scatter plots among all these MSRP 1000, invoice 1000, horsepower, MPG city, MPG highway, and it means group by make. And then I prefer to use that yesterday. I put through the diagonal. I was expecting that histogram for each and every variable. See, 1, 2, 3, 4, 5 variables. And for the histogram should be given with its 2 types of densities. There are 2 types of density. One is called kernel density. The other one called the normal density. Kernel density means like that normally using that kernel smoothing. Like it's not like a smooth curve, but within the interval that we can do the smoothing. Okay, and there are ellipses you can set for the mean. Okay, for the mean, and that part, let's run and see how what we're gonna do. That's the one that we were expecting in that question number 1. Question number 1. That's the one that we were expecting. It's taking such a long time. Okay. See, okay. These are the scatter plot, 2 at a time, 2 at a time, 2 at a time. See, and this is being reflected on the other side, upper triangle. See, in this matrix, and in the diagonal. See, this diagonal we're gonna have that all the histogram being drawn, and then later on they were given with the smooth curve scheme in the top of that one, and another curve just going smoothly going through interval by interval and then connecting to each other. It's not a line. It is not a kind of like a line graph. It's not a line graph, but it has been smoothly taken in a such a way that maximum area being coming under that one. But this normal curve not going to have a maximum area under that curve. See, you can see easily both of them. I prefer to have both of them. So that most of the cases in our the data analytics for mathematical tractability and easiness, what we're gonna do, we're gonna just assume that any distribution, any histogram look like that normally distributed. Okay, so look at their scatter plots. Okay? Scatter plot. Okay? How they were being distributed. See, it's going this way. So this is not going to be even that fitting into a straight line for sure. See, so this being remedied later on, we're going to do that one, but time being they're going to ask us to that creator that scatter plot matrix. We did that one. It has been done with respect to the make. See, different the make of cars. See? So that's why it's been clustered. See, sometimes they see like a big cluster. Look at this being that very nicely that spread out, but these are clusters. But if you have a huge cluster that you don't have any correlation between those two given variables, okay, you can easily see horsepower and this side horsepower, this side MSR. This variable has been regressed with this guy, this guy, this guy, this one, this one. See, this one has been regressed, or that plotted against this one. In a similar fashion, this one has been plotted again. Invoice, you don't do the invoice by invoice. See? So this one, see, it's already done over here. See, horsepower, city, and highway. And on the other hand, that I change even the MPG city to city, MPG highway to highway. But when you're gonna call their variables, make sure that you're gonna call this with the same name being given to them. Okay, don't go with this one. This one. These are like just a label. It's the label because the program doesn't know that if you use a city over here by accident, you say city here and highway. No, it doesn't recognize. It should be given the proper name. It's not case sensitive, but if you have a levels, it's very case sensitive. We had that issue yesterday. We remedied that one. So see the kernel. There are two types of densities, distributions. Density means distribution, kernel distribution and normal distribution. Okay. This one I just showing you that if you want to like create a panel graph of scatter plot, panel one. See, I'm on this one. See, look at here. SG scatter, but it's not for the matrix. You don't use the matrix. You use the plot. See, this versus that, and this versus that has been done with respect to this one. Sometimes if you want, you can have something like that. Do this to that and this to that separately. See, with respect to that group here that make of the cup. Okay. See, you can use that code. See, you can use the plot. See, plot here. Yeah, straight go to the matrix. If these are when this is a data, forget about this label and title. You straight go to the function. See this. is the procedure. And these are extra ones. Okay. So here you plot this versus that, this versus that by make. And on the other hand, if you want that the following code creates a panel graph of scatter plots with shared access, you're going to share the access this time. See, scatter, data, label. Okay, MPG highway, call the highway, then title is scatter plots of the cars data or something like that. Y and X being given, MPG highway being, see, regress with weight, engine size, horsepower, by make at the same time. They don't ask us to do that when I'm showing you that even we can get this done too. See, like that. See, highway. See, that's the same thing you're going to see from that matrix one. But if you want to narrow down that one to that, and if you are particularly interested only in highway versus that these three, that's how you can get this done too. And this one, on the other hand, using the univariate. I'm sorry. See, this one also, see, SG plot. This one SG scatter. See, SG scatter. This one SG scatter. SG scatter. SG scatter. I use here plot. I used here compare. I used here matrix. Matrix, plot, compare. Now I'm going to use SG plot and then put the histogram. Whose histogram? See, MPGCT. I really need the MPGCT histogram. See? Look at here that, see, this one, this for the histogram, okay? These are for the scatter plot. Now I'm going to go to histogram, then I use the SG plot. If you want that single one, I'm sorry. This one, I'm going to go ahead and you can get to see it. This side you can have a percentage of relative frequency. And if you want that smooth curve kernel, that one, you know how to get that one too. Okay, histogram, and then see, same thing we did over here. You can get the kernel and normal. And see, following code creates a combined histogram. See, MPGCT, see, given by group by the drivetrain. Transparency means like opacity of that your the colors scale. Okay, and density. See what kind of a density, what are the densities you need. See, normal density. If you want kernel, you can put kernel. See, key legend and everything, you can get the key legend. You can put the title first and then go to the procedure. So then put that title outside that one. Okay, that's another way of getting this one. See, if you want to draw all the histograms like that with the legend. See, histogram of MPGCT by drivetrain. Drivetrain has 3 levels, all front rear. Those 3 being that embedded within same that frame. See, it's a count means frequency. Okay, count means frequency, and I'm asking for them to put the normal density. If you want kernel, you can put kernel here. See, another way to get this using univariate, you can use the histogram as well. Okay. Here I was giving the midpoints being utilized. See, midpoint, you're gonna say that for when you're gonna draw a histogram, you can take the midpoints or that they are endpoints called the boundaries. So if you use the endpoints starting from 10 to 80, go by 5 units, increments of 5 units. See, midpoint. Next one increase by 5 units. See, 20, 25, 30, 35. See, even the outliers can be easily detected. See, if you can increase that one to 80 or any way you want. See, this is this is not a part of this data set. It's an outlier. and unusual observations. Okay. So then we were interested in looking for the correlation matrix, not the correlation, the scatter plot matrix, correlation matrix. I would really need to get the correlation among that MSRP, invoice, horsepower, MPGCT, this one. See, this one. See? I use something called print comp. Print comp means principal component. We are using that one down the road too, principal component analysis. See? You get the correlation. See? Correlation matrix. So the correlation matrix means what? What's the correlation mean? That's the strength. Here we're gonna see very clearly. I'm gonna just a little bit come back to here. Okay. Let's go to chapter 1. See, okay, let's go to this one and then connect to that one to here and then see at the same time. See, look at this here. That in this slide they say advanced in technology have buried present day managers under a mountain of data. This text has been prepared to give future managers some tools for examining relationship between two or more variables. See, if you are interested in somebody, want to see that how the one variable is going to be related to one variable or several variables or several variable to several variables. We can do that on this multivariate. Multivariate things we don't tackle here because the first we have to tackle, you have only one y and one x or several x. Okay, that's the idea. That's why they say you get a one variable, like you're gonna see the MPGCT being explained by the engine size, or you can add more to that x variable. But engine size, that MPGCT, at the MPGCT, MPG is that highway, and MSRP, invoice, everything you can tackle at the same time too, but we don't do those kind of stuff. So, so those are multivariate. That means that you're gonna tackle one at a time. See? This one to this one. See, let's say that you have one y and one x. I'm sorry, this one. You have one y, one x. Anything, whatever you want to do. Okay, one y and one x. One y and one x. So when we have like this, when you have a data like this, see, you can remember this has been fitted to B0 plus B1x plus 1. Okay, these are called the y. See, these are y. This is his corresponding x. See, so this line gonna go through that x bar as well as y bar. Y bar. See, you can remember up to a certain point. This is called the center or centroid. Center. So this kind of one we're gonna call the simple linear regression. So you have only one y, see, one y. Later on, if you want, you can add more. I'm gonna call this one x1, x2, x3. Let's say that xn. You know, to xn you can add. See, only one y still. That one we're gonna call multiple linear regression. And the top one, since we have a two variable, we sometimes we call the bivariate linear regression as well. See, when you have that so many that x variable, you're not going to have a line. You're not going to have a line. You have something called plane. See, plane. This is the fitted line. It's the fitted line. Okay, it's the fitted hyperplane. It is plane only in three-dimensional hyperplane. How do you write its equation? Y hat equals B0 plus B1 x1 plus B2 x2, see, plus B3 x3 plus dot plus Bn x3. See? You still can write that equation. That's the equation of the plane. Actually, it's the equation of the line. Okay. Fitted hyperplane. Okay, fitted hyperplane. Fitted hyperplane. That's the multiple regression. But we can do like this too. See, we can do several y values. See, y values, several y values. See, y1, y2, y3, and 1x for several legs. See, see, x2, and this one dot 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 ym, and this one x3. This case, this become what? Multivariate. We don't do that. Multivariate. That's the real case. That's how we're gonna tackle at the end of the day. When we be very expert on and then become a data analyst, you cannot tackle only one variable at a time because they're gonna throw so many variables and say that the MPG city, MPG highway, MSRP, invoice. Can you how they all been affected by engine size, the weight, and base length. Oh, that's that all other variables can utilize to explain the other four variables. So we don't do that at this stage. Okay. So here there's a like if you go back to the first one, this one, we get back to simple one, y and x. So we have a line here, we have a dot dot here. We have this guy here, y hat b0 plus b1x. Then we're gonna find that relationship between these two variables. That relationship is called R. R is correlation coefficient or coefficient of correlation. How do you find that one? They're gonna calculate for us. They're gonna calculate for us, but if you have to know what is behind that one. Okay, what is behind that one? You have to know how that can be calculated. How that can be calculated. What you're gonna do? You're gonna do simply R is nothing but summation. You go to summation. You're gonna go to x and x bar. Okay, divided by its standard deviation, and y minus y bar divided by its standard deviation, and then whole thing divided by n minus 1. That would give you. Okay, that's how they calculate this one, where you can say x bar is mean of whatever variable you put x, y bar mean of y. Okay, how do you find the mean of this one? 1 over n, let's say the nx. Okay, nx summation x. Okay? Nx means number of data points in x variable. If this one ny summation y, they've been calculated for us. Okay, so that R correlation coefficient, and then on the other hand is 6 means standard deviation. I'm gonna write this d, see, of x. How they have calculated this one nx minus 1. That means how many variable, how many observation in x variable, see, divided by, say, subtract 1, and you're gonna summation x minus x bar squared. And sy also a standard deviation of y. How do you find it? In y minus, I'm using in subscript y, okay, to say that number of, okay, elements in that one, see, y minus y bar squared. And in next means, see, the sample size of x or number of x observations. And y means sample size of this is the formula that they've been utilized. They calculate through that one. X means like a one at a time. You get the x value, you subtract the mean, and then square. Plus, you get a second x value and subtract x bar, and then square, and then go to third entry, minus mean, and then square, and keep going until that you are done with all the x variables. So that's with this one. Okay. So that's how you're going to calculate that one. And in addition to that one, you saw something here very clearly. Y naught is B naught plus B1 x. Here, where? How could you gonna get the B naught? How they calculate B naught? B naught is nothing but correlation coefficient times Sy over Sx. Sy over Sx. Sorry, B1. Okay, B1. I'm gonna write B1. B1. B1, you're gonna calculate like that. Okay. B1. And B naught is nothing but you can say y bar minus B1 x bar. See, this is y bar y hat. Okay, this is like that. That's how they calculate. They're gonna calculate and give to us. They calculate through this formula. You know S, you know R as of now. You know Sy. See? So this here, I have to make it clear in this case that n here n, I have to tell about the n2. Okay, n is number of pairs. Okay, in this case, this is equivalent to nx, ny. Nx and ny and n, all these three are the same. Okay, all these three are the same. See, nx, ny, and because this is a number of pairs, everything, because we don't have, this can be utilized when you have a two another kind, but in this case, we have a pair. So all these the same thing. N means this is, if you want, you can put the n here. Okay, n here, n here. Okay, I wrote the most general case, but in regression, n and nx and ny all the same thing. That means number of pairs. Okay, number of pairs. How many pairs? Okay, like that. So that's why we have n minus 1 here. Okay, n minus 1. Okay, so that's how they get to that. But keep you in head, this is a very tricky part. This is, they're going to calculate based on your observed sample. Keep in head, observed sample. In addition to observed sample, we have a simulated samples. Simulations can be done through the bootstrapping. Okay, that's why this is not going to be fixed value. You're going to see that one. This is not fixed either. Okay, but anyhow, we were trying to, that's what, let's put it, okay. Those are the formulas for that, get these values. Okay, so let's get back to this one. Have we prepared this one? Some house affected by advertising, what determines the selling price of the house, those kind of a thing. Okay, we can definitely utilize this one to the practical application. See? We are using, this is one of the most important examining, and on the other hand, this can be utilized even for the data mining. Okay, data mining and the supervised machine learning. Okay, so one of the regression processes is supervised machine learning. This is one, and these are, this is trial and error methods. Okay, much statistical analysis, multi-stage process of trial and error. See, they were not perfect. Okay, they are not exact situation, exact solutions. Okay, they are come up with some kind of like an error all the time. There's a good deal of exploratory work. There's several stages, model building and judgment. The emphasis of this text is on the process rather than computation or theory. See, look at it. The emphasis of this text is on the process. It is on the process. We were talking about the process, and computation part we're going to tackle through what? Computation part we tackle through the programming. The programming. We don't go to theory. It has a meaning. This is not theory. I'm not writing theory. These are not called theory. This is not theory. Theory is not this one. You don't know. Theory means that, theory means like how you got B naught, the derivation. You can derive. Those things we don't do theory. This is not theory. This is the process. This is the process. These are formulas. Formulas mean process. Just the formula. These are formulas. That's why this book clearly says formulas. It's processes. See? How you got the B naught? That's theory. That theory we don't do. That's mathematical statistics and probabilistic statistics. Like the heavy that universities like that Ivy League university, they are doing those kind of stuff in large scale, large scale. But now they have some issue too, because that they were now starting with the data analytics. They cannot find the people to teach their classes, because they are most of the faculties are that used to that only theory only, so they don't know how to apply that one to method, that practical application sometimes. So we do this computation part through the programming. Programs do that. Okay. So this process, how this can be gated, and then computation. See, computation is done by the, we're not going to compute anything. No. We don't do computation either. This is not computation. This is not a computation. We don't compute. We don't plug in values and then compute. No. This is the computation tool. See, this is the computation tool. See, we didn't do anything by hand. If you want R, see, you got the R between, see, MSRP and invoice, MSRP in household, and among all these, see, you saw that in this matrix. See, you saw that. And this is another way to get that one too. This is just the this is computation. Computation we don't do by hand. See, that book, they were not showing that how to do that one. See? It's done correlation. See? So this one. Okay. And they were saying about the data. We know that we were always talking about the data. That's why this example and exercise on the CDC. I got all these from the set CD. I have all the data sets too. Pretty much all the data set. They have given all data. Yeah, you can see. Chapter 2 data, see, in all formats: ASCII, eView, Excel, JUMP, Minitab, SAS, SPSS, Stata. In chapter 2, chapter 3, chapter 4, chapter 5, chapter 6, 7, 8, 9, 10, 11. All data. If you need any of these data, let me know that but you can, but it seems that sometimes if you don't have a textbook, you don't have that one. But if you want me to upload all these, just let me know. I can upload that one too. It's not a big deal. Okay. But they were in so many formats. We can at least put that one in Excel form. Then you can get them into the import to the SAS platform and work on it. And then SAS one as well. All the data we have. And PowerPoint slides too, as I mentioned, that they were the one that we are working on right now. See, that's what they were just giving it like a kind of a overview of the textbook. Look at in that chapter 2, they were talking about, okay, basic stuff, okay. Problems, see, statistics want to study in a particular population. That means, like I see, perhaps all firms in an industry or the lifetime of a certain brand of tires. See? The population, whole population. All firms in an industry for the lifetime of a certain brand of tires. See, lifetime, whole lifetime. In most cases, it's not possible to examine the entire population. So we work with the subset of the population called sample. See? If you really want to find that average height of all national university students, you cannot get the population. You don't access, because you can access and then find their height, but you don't do. It's tedious, time consuming, it costs a lot. You don't do. We pick a sample. If you have like 11,000 students, you're going to pick like a sample of other students. This study has 2 phases. In the first, descriptive statistics, the other one called inferential statistics. What that means, you can remember this kind of a discussion you have done earlier. See, they say that if you have a population here, let's say population here, population, I'm going to say abbreviated like this population. From this one, you pick a sample. See, you're going to pick a sample. So how could you going to do this one? You have a sampling techniques, sampling processes. There are so many samples. How could, let's say that you are interested in, you want to know that average, see, average height of all national university students. That's your question. That's the, see, see, you are interested in, see, mu, average, see, height, average height being denoted by mu, okay? Mu. You don't know this guy. See, this is mu. You don't know this one. I would say the population size. Population size means how many student in population denoted by capital, let's say 11,000. 11,000. See, from that one samples, you pick a sample. Now you have a question, how are you going to pick a sample? You go to the classroom, or you're going to send us like a survey online, or anyhow, what would be the best way to pick a sample? And in which the sample has to be very, very representative at the end of the day. How could we going to pick such a sample to that, and nobody will be sidelined, nobody will be neglected, nobody will discriminate, nothing. Everything at the end of the day, you have to make sure that that everybody has in this population being given for that chance to be elected for this sample. If that's the case, what would be, there are so many, almost like 11, 12 that methods that we can utilize in order to pick a sample, random sample. That's random sample is not the best method. The random sample, sometimes that you go to certain cafeteria and pick a student from there, go to the library and pick from 100 students. Let's say we are going to pick a sample size 100, see, sample size 100. Sample size I'm going to denote by simple way. See, 100. See, when you pick anything, this is called anything that you say that you pick a sample size of 100 students using a certain sampling techniques. We have so many samples. Simple sample, see, random sample, random sample. The other one called simple random sample. This one I'm going to say always simple random sample. Stratified sample, cluster, see? Systematic, sequential, like that. Okay, so many methods we have. Out of all these, we pretty much gonna focus on the stratified sample, in which that we're gonna divide the whole university into like a 4 or 5 groups. Let's say based on that, how many that come the credits. Let's say that we are mainly focused on the student that who are doing bachelor's degree, or that based on the student in the master's program. Then based on that one, whether they were in the first 6 months, like if it is a program is for like for 2 years, let's say for 1 year, then you can divide that into 4 quarters, and then say people from the 4 quarters, and then you go divide that into 4 quarters. Or that based on the undergraduates, you can say based on number of credit they have completed, then you can go to the freshmen, sophomore, juniors and seniors, and then divide that into 4 groups. And from each group, you're gonna pick 25, 25, 25, 25 for time being. But that's not the proper way. Because that every subgroup would not gonna contain the same number of students. Like let's say freshman group would not same as that the sophomore group, the number wise. See, so because of that, you have to come up with something called quota sampling technique. This would be based on how many they're gonna be on that one. You can pick like a certain number from each and every group, and 4 groups, and put together to make 100. See, so I'm not gonna get into sampling techniques, but what I'm trying to say, there are so many techniques to pick a sample. Once you pick a sample for these people, you calculate that they are me. See, y bar. That's a sample me. See, that's a sample me. See, that's a sample height. See, there's that average height of 100 students. 100 student, average height of 100 students. This y bar. What they're gonna do, they come back, see, and then make that decision about the population called the inferential statistics. Inferential, to make the decision statistics. That within the sample, whatever you see here called the descriptive statistics. Descriptive statistics. I'm gonna say descriptive stats. See, anything in the sample, whatever that all the quantities, y bar, sample mean, sample median, sample standard deviation, anything called the descriptive statistics. So simply call the statistics. But when you make the inferences, that's called the inferential statistics. Those are the two branches in that. This is the whole thing in the statistics or data analytics. This is the whole thing. But this one involved with the very so much theoretical aspect, computations, and then processes. Okay. That's what they were talking about. In the descriptive analysis, the 5-year return as a July 2002 for a random sample of 83. So random sample, 83 mutual fund. Just look at a list of numbers like this provides a little useful information. Okay. The field of descriptive statistics can provide several ways to meaningfully summarize such list even when there are far more data. You see, descriptive statistics would be the condense that data information about the sample. See, this is the frequency distribution that for each class, how many gonna be over there. See, these are we not do by hand. See, and the histogram there, see, everything we can do by hand. We're not gonna go to detail about that and how they can be done. But histogram means like a graphical representation of the frequency distribution. Frequency distribution means that when you have like a huge data set, you can condense that data into classes. These are called classes. And this means the frequency, how many times it has occurred, how many data points going to be within that particular this one. And then they go to something called the box plot. See, box plot will show you that see the summaries as another summary statistic. See this one, see minimum, this is the minimum. This is called the whiskers. See, this upper whisker, lower whisker. The box, the mean, this one is the median. This is called the quartile 3, third quartile, or the 75th percentile. This is the first quartile, called the 25th percentile. This is the median, or the 50th percentile, or the second quartile. See, mean gonna be somewhere here. You know that. See, so there's another way to represent that. And these three, if you get the minimum, maximum, first quartile, second quartile, and third quartile, that's called the 5-number summary. I'm talking about minimum, maximum, Q2, Q1, Q2, Q3. Those 5-number called the 5-number summary. Okay, but we don't go to detail on that. Then these are discrete random probability distribution, means those are that smooth curve. Okay, sweet. We don't need that much of this one. Okay, this is how they're going to calculate the probabilities. Yeah, probabilities. Okay, so we don't have that much time to go through. This is the profit from the investment. This is coming along with this the probability. How much? What is the chance of that they were having this kind of a negative 2000, negative 1000? See, losses thing with the probability. Because we don't know exactly that how much we're gonna make. So because of that, we're gonna incorporate the probability in this one. Then how do you find the expectation? Expected that value of this one by multiplying these and then sum them up. That means you're gonna multiply this time that, this time that, this time that, this time that, this time this, and then add them up. So that's with this one. Okay. Those are just the basic stuff. That's what they were doing here. Okay, interpretation, this one you might not gonna need it too much. Okay, you might have done all this at a certain point. See, normal distribution come into the picture. Normal distribution is a bell-shaped distribution. See, it has its mean at the center. This is a spread. Spread is given by the sigma. See, standard deviation, population standard deviation, population mean. See? It's not an individual observation. It's a collection of all height or whatever the investment or income or whatever that we that denoted with represented by a certain curve. So it's going to represent the whole population. That's why we're going to call the population mean, population standard deviation. Okay. Normal probabilities. Okay. I think those kind of stuff you have done already. How to standardize, get the value and subtract the mean and divide it by the standard deviation will give that one. Basic stuff. Those are basic stuff. Okay. Distributional form. And these are is how you're going to find that the confidence interval. Okay, when we come to that one, let's talk about that one, but I think mainly confidence intervals to find the estimate. It's called interval estimates, standard error. Okay, those things you can read. There are a lot of stuff in all this because we cannot go through all of these, because the thing is that this book is meant for like a 15 weeks. Within like a 2 weeks, they're gonna go through this one. But I assume that you guys have done this kind of a setting. These are the ones that I was setting up when I see that the problem. Can you remember? Then I mentioned about the T. Okay, we can go through them appropriately. Okay, I will just show you that. See, so many here behind that one. See, so many of them. See. Then you're going to compare two samples. See, this is the one that I'm going to come to this one. This is the one we related to our homework, and this one too. Okay, number two, and this one too. We will talk about that one at a certain point, and we can talk about this one as well. Degrees of freedom. Okay. So when we set up in our, when we go back to our problems, and whenever and wherever the necessity rises, that we can go through that one. Okay, so let's get back to here. Okay, then I ran the regression too. Regression means like I was trying to get the regression for that at this stage. You're gonna have the same question for chapter number 3 too, but here see, I ran this one is 2 ways using GLM, and then I'm still on number 1. See, MPGCT and engine side. CL parameter means confidence interval for the parameters. I'll show you what this gonna be. Okay, I'll show you. See, look at this one. The procedure would be seen. You have to say model. This is Y variable. This is X variable. Okay. When you run regression, you get all these. Okay. You get all. You get B naught. See, this is B naught. We don't do the calculation by hand. See, we do not do the computation here. We were just talking about the process. Process say B naught is being given by Y bar minus B1. Next, B1 is given by correlation coefficient between that Y and X and times the SY over 6. That part has been already calculated for us. See? And then B1 has been calculated. See? Both calculated. So these are their standard errors. What that means that you see, they are intercepts. See? The standard error of this guy, standard error of this one, and t-value of this one, and probability of this one, confidence interval of this one. Those are the ones that you have to get a clear idea. Okay, so that what I'm trying to say that, okay, in our discussion, okay, this is related to that. This is what we're gonna do throughout this whole course. We go to simple linear regression. You can remember I built up this one. I call this one X, this one Y, and then I have this line. Then I say it's gonna go through Y bar. Okay, for sure. This is its counterpart X bar here. Okay, this is Y hat. Y hat, you know how to get the value for B0 and B1. We know that one. Let's pick a value from here, Y. And then we were talking about 3 different deviations. Can you remember last time we did that? 3 deviations. This point is Y hat. This point is Y bar. See? You can remember I was talking about sum of square total. Sum of square total, SST. SST is nothing but Y to Y bar. Y to Y bar. See? And then square. And then sum them up for all the data points. And the sum of square regression R is nothing but how much. See, this is empty model. You can remember empty model. Empty model is with respect to what? Y bar. This is the regression model. See, this is the regression model. When you introduce the regression model, your error has been reduced up to certain point. See, it's been shifted. See, it's been shifted. By how much shifted is called the sum of squared regression. It's been shifted y hat minus y bar by that much. And then we're going to square to that, prevent that they become zero. Okay. When you sum them up, otherwise they become zero. See, the other one is sum of squared error. Error is nothing but y minus y hat for sure. See,
Hey, Professor. Professor.
Playing a heavy role. And they were connected like this.
Can you hear me?
SSP is nothing but SSR plus SS.
I can hear you.
Composition,
I think he's just muted.
Yeah, he can't hear us. I'll just try to raise my hand and see if this is it.
Sum of squares. They govern that whole regression setting. Okay. So here, what's going to happen that if you go to this the R node like that, see, if you go to error, see, we can see something called this one. Okay, we need that the B. I'm gonna write this one. We here. We did this one up to a certain extent, but I'm gonna do one more time for you to get a clear idea, because this is the whole discussion you're gonna have for whole time. Okay, here this is called sample version. This is called the population version for the same thing. For a given any x, you have a distribution, not a values. Here in sample, you have values like these dots. For a given dots. So here we think that for a given value, there are so many y values for a given x. Let's say that you are interested in MSRP and engine size. For a given engine size, they think like you have so many MSRPs here, infinitely maybe. They've been modeled by a distribution. But here maybe one or two, or maybe none sometimes, see, for that particular value. See, that's why they will scatter like this, scatter like that. Not like this form. They are not in population version, they go one at a time. So if you do like that, they believe that the another distribution. They go to their center. See, center. Center. Those centers are connected. The center is nothing but mu of y. See, y me, which is, see, I'm not gonna say y bar because the y bar is here. See, y bar here. In that, in this setting. This is x bar. This is y bar here in sample version. Here we can denote with the mu y. Or I can use another notation called expected value of y. Expected value of y. Therefore, that equation we're going to write this way. Ey equals beta naught plus beta 1x. That's how I'm going to write the equation. Equation of the regression line. In a similar fashion, I'm going to write the equation of the zinc. I'm going to put a new cartridge. Equation of the regression line. You're going to write with the y hat equals b naught plus b1x. See the difference. See the difference. See the difference. Oh, okay. Yeah. Go ahead. And Angela, go ahead. I'm sorry, I didn't see that one.
Okay. Can you hear me now?
Oops. Okay. Give me 1 second. Okay. Go ahead. I'm sorry. Go ahead now.
You can hear me?
Yeah. Now I can hear.
Okay. I just saw you were attempting question 4 using the GLM, the proc GLM function. I use proc reg and I compared the results and they seem to give me like the same information. Is there a reason I shouldn't use proc reg here?
Yeah, you can use the proc reg. That's what we were using, because we were using that. Even if you go to 4, let's see, number 4, see,
Oh,
So
yes. Right there, you're using GLM, and right there, you're
yeah,
using.
GLM and proc that I interchangeably use it, but there's a
Okay. I was
huge
just making sure. I was seeing the same results using both of them. So I was just making sure that it's okay with you, that it doesn't matter which function we're using, as long as we're getting to the right information.
exactly. Mainly that this part gonna be the same, but here we have these are the parts we have to discuss throughout that whole the course. You're gonna see this one. See, look at here. They call the type 1, type 2 like that. According to this textbook, the textbook that they have utilized. Okay, so I have to stick to that one. So that it involves with some explanation for that one. Those are the one I'm trying to get into right now. Yeah, that I'm gonna explain that one, and you're gonna see that one down the road again too. But doesn't matter. We can explain here at this stage, and then it's gonna be clear. So what
Okay,
I'm yeah.
just making sure that it's a
No,
that
you're on
that
the right track. You are on the very right track. Yeah,
yeah,
you're on
just
the
a.
very right. Sorry that I didn't see you because I was so much into that explaining this one.
It's okay. We figured you'd look up at some point.
Yeah. So then in this one, that look at that. We use the beta naught. In another way, we can say the B naught is an estimate of beta naught. That's what we are trying to say. That's the key part in this one, estimation. All statistics and data analytics are all about the estimation. We estimate because we don't have exact value, because we cannot go over here. We don't have a population. We don't have a population. It's a more theoretical abstract. It's something that we made up, and we assume that it was like that based on that past experience, and then experimentalist and data analyst, and then all kind of a statistician, they experts, they utilize in the heavy mathematics, they came up with this kind of format. But those things we don't do. We have to simply say that we can, based on my observed sample, okay, key part here, very careful, this observed sample is a key part. Observed, I'm going to use observed. In addition to that one, you can get the simulated sample, many samples with the aid of the observed sample. That's the process called the simulation. You simulate with the aid of that one. That's why some people, they say that they cook the data. They don't need the real data. Sometimes they can cook the data. They can artificially that induce data. And then these days, that especially that's why that we have a serious issue with the nowadays, that especially with the COVID cases, some data where they come or they were artificially create nobody knows what's going on. But anyhow, that some sources we have to rely on some sources, and then make sure that we go with those theoretical aspects, because sometimes some data, most of the time, they induce data. Practically, if you go to some place and they collect data and then keep with that one, that's a different thing. Okay, collection of data is a huge process. But B1 is an estimate of beta 1. See, that's what we have to tell him. Then you know, B not how the formula, the process you know now. We don't have to go back to that one. You know the process. This formula you know. You don't compute. Computation is done by the program. And you get the answer and you put it back into that one. See? So you have to get an idea behind that one and say this is an estimate. And on the other hand, then they were not interested. What we are trying to say that if you get a beta naught is I'm going to add this one and little bit change, and is a point estimate. See, I'm going to add that word. It's a point estimate. I'm going to put an emphasis on that one. Point estimate of data. Practitioners say, I'm not interested in only in that point estimate. Give me the interval estimate. Give me the whole bunch of values, not a one value, not a one value calculated from this formula. They were not happy about that. This is a one value. You know standard deviation of y, you know standard deviation of x, you know correlation between y and x, and then put over here to the formula, you can easily get the answer. They say no. We need more than that one. In order to do that one, I'm interested in what? I'm interested in something called the interval estimate. Interval estimate of beta naught. I'm interested in interval estimate. That one I'm going to denote like this way. See, I'm going to write the CI. CI standard for confidence interval for data node at a certain level. I'm going to say 0.95. I'm going to talk about that one later. How could we going to get this level? That means you get the interval. Interval has a lower bound and upper bound. See, interval has a lower bound and upper bound. See, lower bound, comma, upper bound. This is for the lower bound, lower boundary or bound or limit. This one upper bound. All the numbers going to be between those two. This one stands for confidence interval. We call that one confidence interval of data node with the confidence, with the 95% confidence. That's what we use. That's how we got the 95%. It may be anything with a certain confidence. You have to give this one. In that way, we call this one the level of confidence. Level of confidence. Okay? 0.95. Level of confidence is 0.95. See? It's called the level. See, how do you get the lower bound is the key part. Now you need the lower bound. We don't calculate it. They do that one for us. We have to get the idea about the process only here, as we did earlier. How do you get that one? You go to lower bound. Okay. How do you get? You go to B naught. You're gonna put the subtract something called T value. Okay? It's based on T. Okay. When you T value, this is called the T critical. I'm gonna put T critical. T critical T value. I'll show you what that means. Times standard error. Okay, standard error of E naught. T critical means they're going to fit into a T distribution. Just a zero here. And they were thinking about everything going to be bit here. 0.95 going to go to here. The leftover going to go here. 0.05 divided by 2.425 here. And 0.025 here. See? These are the bounds. See? This is the lower bound. This is the upper bound. See? See? Anything, T values, even that we have to find out the T value and plug in into that one. So your TC should be, okay, related to this one. I'm going to put TC here. Okay, negative TC here. So I get rid of this one because I was just showing you together. That's how you get the lower bound. It's not merely lower bound. It has to be that get the TC and multiply this one and then subtract from this one. Then you get the lower bound. But to get a rough idea, I just say that lower bound for you to. Okay. That's another one inside. So we go with this one. See, this is TC. See, critical T value. How do you get that one? They calculate that one. See, they calculate that one. Critical T value, they calculate. And they get that one. And how do you get the standard error of B naught? Standard error. See, standard error of B naught means standard deviation of B naught. You know the reason why that B naught is like that. If you go to a population, from a population, if you pick a sample one of size, let's say N, you calculate B naught. You can calculate B naught. Let's say that that's the you observe sample. We're not gonna happy about only one sample. In order to create that interval estimates, you pick another sample. Sample two of the same size same. And you calculate that one too, B naught too. In order to put that one, I'm going to put like this way for you for the convenience. Second one. And if you keep doing this one, let's say you do this one 1,000 times, sample 1,000 of size same size. You can say 100, whatever the size of the sample. See? Calculate again. B naught, you can calculate, yes, 1,000 times. See? These will differ from each other. That will constitute some kind of a randomness. See, then what we're gonna do, You're going to draw the histogram of that guy. Then you get the smooth curve scheme in that one. Then you go to its center. You're going to say mu, mean of B naught. See, I'm going to denote like this. Say, mean of B naught is same as B naught. That's what the theory says. Mean of B naught is same. That's the notation, B naught. And this spread, standard deviation of B naught, is the one we call the standard error of B naught. That's the one we are trying to find out. Standard error of B naught is what? How do you find the standard error of B? Standard error of B naught, I'm going to write over here for you to see. Standard error of B naught is, you're going to get S, I'm going to write S square root. You don't have to worry about this one. No way. N is that number of pairs plus x bar square divided by summation x minus x bar whole thing square. What is this S? What is this S? This S is the error of standard S. How will you calculate? Calculate S here. S is, I'm going to say S would be nothing but sum of squared error. Sum of squared error divided by degrees of freedom of error. That means sum of squared error. You know how to calculate, divided by n minus degrees of freedom is number of parameters in the that okay? Number of parameters. In our case, we have n minus 2. See, 2 parameters. So I'm going to divide by that. When you divide that by that, we call that one mean squared error. See? Mean, we talk about that one in first place, mean squared error. See? So you should have its square root, okay? Square root, see? Within square root. Square root. So you get the mean squared error. We don't do anything, okay? I'm just showing you the process only. I'm just showing the process only. When you take the root, its name is root mean squared error, RMSE. RMSE. See, RMSE means root mean squared error. That's the one they were. Sorry, I'm gonna write this one very clearly. RMSE. That's S has been utilized to calculate this one. We don't do that one. They will do. They will do, and they're gonna subtract. See, to calculate lower bound. See, that's how you get it. See? You know how to get the B naught. You know how to get TC. They will do that one for us. We know that what's going on when it comes to the TC means the critical C. See, critical C based on the, see, this is the level of confidence. Okay. This both side together, this 0.5, I'm gonna call level of significance. Level of significance. Level of significance. 0.5 only, 0.05. Whatever left over from the level of confidence, or this being distributed on both, that on either side doesn't matter. It doesn't matter when you put together 0.05 for the level of significance. Then you know how to get this one, right? That's the formula behind that one. There S would be that one. And how do you get this upper bound? See, upper bound, you can write the upper bound here too. See, upper bound is nothing but, see, V naught plus TC, standard error of V naught. When you come to that, the T distribution, it's completely defined by degrees of freedom, DF something called. That degrees of freedom is nothing but the degrees of freedom of error, which is n minus 2. n minus 2. Okay, n minus 2. Always n minus 2. Okay, that's the part you have to keep in head. See, so in a similar fashion, we don't have to draw this one. You get one idea for the B naught, that same idea, how we got this the randomness of the B naught through this process. We don't have all these B naughts. Keep in head, we have only one B naught because that B naught is from our observed sample only. But we simulate, we assume that as if someone else has done this one and got different value, how this can be, how we going to accommodate that one in our model. You should accommodate that everybody's ideas, everybody's values. That's what we call the model. Otherwise, it's not a model. It's like a very restricted model. No, model should be for everybody. Anything should accommodate that one. That's why for the model, they were thinking, oh, someone else might have to come up with somewhere different value for B naught. Let's say it's 5. Somebody may be 6, somebody may be 8, like that. Okay, for you, just for the sake of giving a number. And that randomness, that variation creates some kind of a histogram for that guy, and is the spread. Okay, that spread and that center. This is a center. See, I'm using the center of that histogram. I'm not doing anything magical. See, I'm using the center and see that how these be not clustered around the center. That's all I'm trying to do. That's the way that how they've been distributed has been given like this way called the confidence level. Those are the confidence level you're going to see here very clearly. See, it's been calculated for us. We don't have to worry about that. We don't do computation. We don't do calculation. Computation done by the program. We're going to show you that formula. Formula means the process. Theory we don't cover. We not theory because I'm not sure how we got that one. We don't do. See, we have confidence in lower bound, upper bound, lower bound, upper bound. See, standard error. This is the standard error. It's a standard error. This is a TC. It's a TC. So this is a T value. It's okay. This is a T value. Sorry, this one is not TC. Okay, I'm sorry. This one is not TC. I'm gonna go back to that one and show you what T value in that. Okay, so here you see TC. We got the TC in order to get the lower bound and upper bound. But if you go back to that, this guy again, I'm gonna go to T again. Okay, I'm gonna go to T again, and I'm gonna utilize something like this. I'm gonna think B naught. Okay, I'm gonna have a testing. Okay, I'm gonna go to testing. Okay, this is related testing. This is my testing. I'm gonna assume that beta, there's no beta naught versus its counterpart, beta naught not equal to 0. In order to run this test, you need some kind of a test variable. This is called the test variable, or you can call the test statistic. In our case, this is the T statistic. See? That's a T statistic. It's given by B naught minus beta naught divided by standard error of beta naught, B naught, I'm sorry, not the beta. That's the formula. B naught. B naught. That's the formula. So we're gonna calculate this one. Now we're gonna calculate this one under H naught. Under H naught means assuming that H naught is true. I'm gonna think H naught is true. If H naught is true, you're gonna come up with what? I'm gonna make this one. If you want, you can say T. I'm gonna put T naught. Okay, simple T naught to say that observed. Okay, it's another name. Observed. Observed T value. Another name. Calculated T value. So many names. Then under H naught, this T naught become what? B naught over standard error of B naught. That's how you got this one. That means here in this thing, you have to estimate B naught. You have its standard error. when you divide 30.77 by 0.54, get this one. So let's see. 30 point, I'm gonna say 30.78 divided by 0.55, two decimal places. Yeah, it's gonna be 0.5596. That means it's gonna be 56. Okay. When you add with all the decimals, you're gonna get this value. See, that's how you get it. This divide by that, you get this. Now, how do you get this one? Probability. In order to get the probability, okay, that's how you get that one. See, T naught is B naught over that one. P naught, P naught you have. T naught means the observed T. I'm going to call this standard error of V naught. It's already there. Then I'm interested in what? They say that if by any chance I'm going to locate my T naught here, look at T naught here, and minus T naught this side, not the TC. This area, those areas, sum of those two areas, that means the P value is nothing but the probability that T extreme T naught plus probability T extreme negative T naught. Sum of those two. That T value being calculated. Probability T greater than positive T naught plus probability T greater than T naught. That means you are just calculating this shaded region. It's not TC. It's with respect to T naught. T naught means observed T. Okay. How do you get the observed T? Through this formula. It's a process. Then by looking at the P value, you can decide if P value is extremely small or is less than the level of significance. You know level of significance. Okay. I'm going to denote level of this significance for the first time with alpha. Okay. That means that in this P, if you go to the confidence region, you have here alpha over 2, which is 0.05 over 2, which is 0.25. This one is alpha over 2, which is 0.05 divided by 2, 0.425. This one is 1 minus alpha, which is 0.95. So 1 minus alpha is a level of confidence. Alpha is level of significance. We reject, which is 0.05. Okay, 0.05. We reject H naught. H naught, you can say at alpha 0.05 if you want to complete it at that level. Because when you're gonna reject that, whatever you hypothesized, if you reject, this is the criteria, like in a courthouse. Okay, some people come here, see, whether they've been, see, the defendant is innocent versus he's been tested against, he's been the culprit or something like that. The courthouse is tied to that, built up the evidence. Those are called the data, built up the evidence to reject H naught. That's what they are trying to do. They were trying to, anyhow, they try their best to that, prove that and say this person is not innocent. That's their process. That's the legal process. So they the same way, if they do like that, we're gonna call that one the test is significant. If that's the case, see, if H naught is rejected, we say that the test is significant. So they do like this. So we don't do anything by hand. We don't have. I'm just showing you the process behind that one, and then to interpret. This is how you get the p value by looking at the p value. Looking at the p value, what are you gonna do? If you have to run test for this guy individually, not overall, you can do that one. So does with this one. Same discussion you can build up for this one. I don't have to write that one. You know, the same discussion. In a similar fashion, only thing that is for the subtract, so the subscript that you have to change this one to 1. That's it. Okay. When I do for this one, you know that similar discussion can be added to the other one. Only difference, only thing I have to say over here that you know this one, you know standard error of B naught. It looks like that. The standard error of B1, okay, only thing that I'm gonna write over here, standard error of B0. Then now if you want confidence interval for B1, sorry, beta 1 at 0.95 or 1 minus alpha, you can say it's lower bound. See, lower bound is what? B1 and the plus or minus. There's another way of writing this one, okay? TC, okay, times standard error of B1. Yeah, there's another way of writing this. This is the same thing, okay? That's the same thing I wrote earlier, minus TC times SEB1, comma, B1 plus TC SC times SCB1. That's the same thing, okay? That's the same thing. So where SEB1 is what? SEB1 is nothing but S times 1 over square root summation x minus x bar squared. S, you know S, you know S. S is nothing but S is root mean squared error. That's the one that you're going to see here. So the same thing that you can apply to the number 4, because even though I discussed this one in number 1, you can apply the same thing to number 4. Okay, that's the idea. See, that's how you get the confidence. See? All this chart you can easily explain. And these are the estimate. They're not happy with this one. They say, give me the range. See, range of values, range of B naught values. B1 is utilized in order to calculate that one. We got this one by dividing this by that, we got that one, then finding the probability against this one, we found this one. Okay. Like that. So that here the ELM I was just running and see. Then I did the same thing with the reg. See? Sorry, it didn't go through. Oh. Okay. So this time we don't have a type 1, type 2, type 3 like that. The other major thing that I want you to focus on this one for regression. The same thing, that same discussion you can just extend to that when it comes to the number 4. Okay. See this one, ANOVA table. You can remember we did this one the other day. We did in the very beginning this one. ANOVA table. Can you remember? You have an ANOVA table here. Certain point I put things I can remember. See, anyhow, see, we can build up that one for this regression. See, that's the one that you have to read too. Oh, sorry, this one. This one. See, analysis of variance table for regression. Regression. See, and this table, this one too. See. So, what that means? What is that? See, and here that if I write even that's for the t. You get the t value. See? So you can what about that this table? Okay, this table. This ANOVA table, ANOVA analysis of variance table. You can remember here you have a source, You have a model. Model means regression. Regression. Then you have error. Then you have a total. Then you have a degrees of freedom. You can remember model degrees of freedom, DFM or DFR. I'm going to say DFR. DFR is nothing but number of regressive variable. We have only one number of regressive variable. See, I gave that formula the other day. Degrees of this one is what? N minus P. I'm going to say this one Q for you to Q. Okay, this one P, and this one total is what? N minus 1. N minus. So Q means number of explanatory variable, number of explanatory, that means X variables. How many X variables is there? This one. Okay. In this case, we have one. P means number of parameters in the model. See? We have, you know, this is our model. Y equals beta naught plus beta 1x plus error. Error, I'm going to say epsilon. Okay. Epsilon in population version. I wrote the population version. Okay. 2 number of parameters. This one is in our example. This one is 1. This one in our example. This one is 2. See? Then we have what? We have a sum of squared. Sum of squared means sum of squared error. Sum of squared regression. Sum of squared error. Sum of squared total. Then we have something called mean squared, MS. MSR is nothing but SM, sum of squared regression divided by degrees of freedom of regression. This one is mean squared error is nothing but sum of squared error divided by degrees of freedom of error. Then you have F. F is means like I'm going to take F naught, okay, F variable. Mean squared regression divided by mean squared error. Then this one fitting into something called F distribution. This one you have a P value. P value is nothing but probability your F value greater than F naught, not double F naught. What that means? That means if you have a F distribution, something like this, F, and you go to the F naught, and you're going to find the area to the right of the probability F greater than F naught. Observe there. Call the P value. That P value you can utilize to check that regression too. To do what? One test for this one, H naught, beta 1 equals to this one versus HA beta 1 not equals to this one can be tested by either t-test or f-test. What do you mean by t-test? Let's go to t-test. First one, t-test. T-test, we have a t. T means we have a what? B1 minus beta 1 over standard error of B1. See? Now on the H naught, this become B1 over SC B1. You know, we did that like that for the other one. The other one called F. If you go to F, is nothing but mean squared error over mean squared regression over mean squared error. See? That's that. See? You can use either T1 or F1 by looking at that P value related to in this ANOVA table. Look at the go to the ANOVA table. The P value. Again, based on that one, this P value is what? This divided by that, give this one, this divided by degrees of freedom, give this one, and this divided by that, give you that one, and finding probability, give this one. See? That's how you're gonna read that ANOVA table. But when you run that one, see, if from that, or you can use the t-test. So it's this one. See, you can use the t-test. See, see, intercept. See. Go over here. See, intercept. Intercept t-test. P value or overall P value. But if you want to check for the B naught you can do from here, not from here. This for the overall test. Overall test. And then we have another one called R squared. R squared playing a heavy role, very heavy role. R squared is very heavy role. R squared is the key part we're going to look into to see whether this is going to be big, the proper model or not. It's a one of the method. R squared is nothing but, you know, this one. This is nothing but sum of squared error carried from the empty model. Okay. Even though we write like this way, this is a sum of squared error. We were carrying 11,716 units from the empty model. That cannot be explained by that one. You know that there's an issue over here. You have, I think, learned about that error. Error playing a heavy role. It's called the white noise. Okay, that one you cannot remember. When you write this y equals beta naught plus beta 1 x plus epsilon, that's a population version. Okay. Oh, if sample version, corresponding sample version, I write y equals b naught plus b1x plus e. In either one of these cases, this error is, look at the error. If I write this one, this table, again, I'm gonna write this one. Okay, this table, especially I'm gonna put this source, and I'm really interested in sum of square. Okay, so this one is regression. This one is the error. This one is the total. What that means? Total sum of squared means SST, SSAE, SSR. This is nothing but sum of squared error unexplained. See, unexplained leftover, unexplained sum of squared error leftover. Sorry, unexplained leftover sum of squared error from the empty model. It's coming from the empty model actually. This is unexplained leftover sum of squared error from the empty model. This one is sum of squared, see, explain. Sorry, this one is explain sum of squared error by the model. By the model. That's a sum of squared error too. This one is what? See, unexplained again. Unexplained. Unexplained. See, leftover sum of squared error from the regression model. Regression model. All are errors. Errors being explained. Then unexplained and explained. What that means that when it's come to the error, error can be, see, error, you know that error error can be what? Explain and unexplained. Explain, see, explain and unexplained. Unexplained. Yes, unexplained error and this one divided into two. There's a say within the system. The error due to within the system. When you're gonna measure something, let's say that measuring tape. Measuring tape has some kind of error. It's called intrinsic error. See? Intrinsic error. Error of the system. Or you have an extrinsic error. That error means what? Induced error. Induced error. Due to what? Due to what? Due to sampling. When you do the sampling, you make the error. Due to what? measurements, measurement error. The other one, uh, the human error, mistakes. Sorry, mistakes. You have entered data wrongly. You have entered data wrong. So you can see this is how it works. So when you pick the sample, how come we're gonna make error when you pick a sample? Let's say that you wanna pick a you're gonna find that average height of all national university students. Sometimes you're gonna be biased in and get all the tallest one only for the sample, or the shortest one only, or the people in the medium that height of the high people only. That kind of a thing gonna happen. Sometime it's gonna happen. Okay, because of that reason, you're gonna have some kind of an extrinsic error called the induced error, which cannot be explained because it is within that one already. Or measurement error. When you're gonna measure, let's say that you have to measure that the height, you measure that one. Different way that I mean like sometimes that when you're going to measure that, let's say that for instance that if you want to measure that thumb length, sometimes that thumb length, some people let's say that measuring sometimes look, let's say height, let's go to the height. For the height sometimes they see sometimes go to that level. Some people go halfway through, mistakes. They don't go to all the way up to that one because of the hair or something like that. Sometimes they're going to measure all the way to the forehead. Some people go to the top of all the way up to that hair, like that kind of error. Mistakes means like when you're going to enter data, instead of putting with the let's say meters, sometimes you put the centimeters. Sometimes you put the inches, instead of putting inches, you put the centimeters, meters, like that kind of a mistake. So numbers, mistakes, those kind of those are within, those are unexplained errors. So here we have explain error is good. This much been explained. That's why we are using the model, regression model. Then we see how much been explained. Look at this one. How much been explained? I'm sorry, here. You carry this one from the leftover, unexplained leftover 11,000, but only 5,897, see, been explained. Almost like a half of that one being left over again. That's why this is 50%. That means it says something very clearly. R squared is nothing but R squared is nothing but R squared is nothing but R squared. See, you can say R squared is nothing but this has another name, PRE. PRE means proportional reduction in error. How much error being reduced due to this particular model. If that's not going to do a better job, then we move on to another kind of model. That is nothing but sum of square regression divided by sum of square total. Sum of square regression divided by sum of square total. We know the relationship between sum of square, some SSR, SSE, and SST. I'm going to replace SSR with the SST minus SSE. That's the same thing. And then I'm going to divide SST by SST here minus SSE divided by SST. It's nothing but 1 minus SSE over SST. Another way. That's the R squared. See, R squared. And on the other hand, see, there's the same thing, R squared, 3. Okay. So R squared is 3. If you want, you can keep as like a percentage. Okay. So if there is only one x variable that is for the simple linear regression. If you get the simple law, which is correlation coefficient, we know how to get that one too. It's nothing but the square root of R squared. So nothing but square root of P. It's it's valid only for the simple linear regression. See, only for simple linear regression. You can see that. See. So that's why they have, and it's been adjusted. This adjustment is not that much feasible over here. Why they're gonna adjust it, that one? They can adjust that one very clearly. When you're gonna adjust that one, you're gonna subtract, because that sometimes it's this is, I think we can talk about that one in multiple regression, because in the multiple regression, for the sake of that improving that regression model, you're gonna throw so many x variables, but some x variable not gonna explain the variation in y. Even if that does not explain, you still keep throwing that some kind of that see, some kind of that x variable. Okay, you're gonna throw x variable. See? So R squared has another name too, and KRE is called the correlation. Sorry, determination, correlation of correlation, no, coefficient of determination, coefficient of determination. That's the one determining that model at the end of the day. What determination? Coefficient of determination. R squared, R squared, R squared, coefficient of determination. So as the simple regression, then that should be the correlation, correlation coefficient. Simple, simple. That if it is simple one, if it then is come to the many variables, it's not the case. Okay, that's not the case. Then it's gonna change to different things. It's gonna do different things. Then let's look at that this one. Let me see. Yeah, we can look into tested R squared. When it comes to that, yeah, we can do that one when it comes to that overall. Sorry. We keep like this one. Okay. Mainly because here the adjusted one is the same as this one. And see, these are root mean squared. See, root mean squared. See, dependent variables mean. See, coefficient of variation. The coefficient of variation means what? Coefficient of variation means, see, coefficient of variation. Variation means standard deviation divided by mean. Sorry, sigma over sigma. If you want to, you can say S over I bar or X bar depend on that. Y bar. See, Sy over Y bar. I'm gonna get rid of this one. I'm gonna write this one clearly. That part you can read. See, Sy over Y bar. That's the coefficient of variation. How a standard deviation going to change with respect to that mean, with respect to mean. That means that you can this one, the general one, you can say standard deviation over mean. Coefficient of variation, that's called CV. That part we have over here. So that's mainly that part. Okay, and then this one, yeah, we can read this one. We can read, see, this one we have, see, observation used one. They have used the whole thing in that particular case. Okay, so a little bit we go further down. Okay, this based on that. Then go to the t-test. In the t-test, we talk about that one the other day. I'm gonna run this one for one, and then similar fashion you can build up for others. Okay, let's run the t-test between the two and then say that how they differ from each other. See, whether they are, see, when they say that their mileage, okay, either mileage in the city or mileage in that all of front wheel, whether they are the same. See, this discussion we built up the other day. Can you remember that we have this one? We want to test this one. Okay, this based on number two. Number two, you want to test mu of front wheel, mu of all wheel versus HA, mu front wheel, gonna be mu A. See? This means what? Average mileage. Average mileage for which mileage? Any mileage, MPG city. Let's say the MPG city for front wheel driven cars. And the similar fashion, you can say A for the all, okay? Average mileage. This is the one we're gonna test. In order to test, you really need something called the T again. T is nothing but, okay, Y bar of front wheel minus Y bar, because I'm gonna write this one equivalently. Same thing, I can write this on H naught. I'm gonna bring to one side. The difference equals 0 versus difference not equals 0. You can write like that way too. See, that's another way of writing. See? Because of that, we're gonna get the difference between this one, see, front wheel and all wheel, see, minus mu f minus mu a, see, divided by standard error of y bar f minus y bar a. Then under H naught, you know, again, under H naught means assuming that H naught is true, T is nothing but y bar f minus y bar a divided by standard error of that same value. Y bar a. Now, how do you get the standard error? How do you get the standard error? You have to get the standard error in two ways. We showed that one, standard error. See? Standard error of y bar minus y bar a if can be two ways. One, assuming that sigma 1, sigma f, that means the distribution of this guy. That means the variance of front wheel equals to variance of the distribution of all wheel 1 or not equal to. See? F not equals to this guy. This one we call the pool one. See, pool. This one we call the setup rate. Setup rate. Unequal. We don't know yet whether unequal or equal. It's a different discussion. Setup rate. How do you get this one? If they're equal, I'm going to go ahead and take something called SP square root 1 over N of the front wheel, 1 over NA for the all wheel. And where SP is nothing but pool standard deviation. How do you calculate? NF minus 1 times its standard deviation. See? Sorry, variance plus NA minus 1 S squared A divided by NF plus NA minus 2.
Can you hear me?
Minus 2 divided by square root. Everything they calculate for us, we don't have to worry about it. This one is nothing but see, SF squared over NA, NF plus SA squared over NA. They get the variances divided by its own sample size. If you compare two, they both have not the same thing. In the regression, you have the same number because that's for the pair or X and Y. Here, two Y's you're going to compare. Okay, two Y's you're going to compare. Here. Yeah. Okay. Yeah, I can hear. Go ahead, Angela. Thank you.
Okay, all right, so you had me, but the math is, I'm getting a little lost in the math. I was not a math major. I
No, no,
don't.
no, don't worry about those equation, anything, because I have, because of the, you don't even memorize or don't do anything. Because on my side, I have to show you because of that's the part of this course.
For sure.
Yeah.
And so I think I was reading up on, I was just reading up on how to interpret the t-test results from Proc, or from, Proc Reg, or whatever that is. And I think it's set. So I think what I'm understanding here is that you use the pooled value for when the means are equal to each other. So we are rejecting the null hypothesis, or no, we're accepting the null hypothesis in that case. And the Satif, what is that called? Sorry.
Yeah.
And that one, it should be for when we are accepting, or when we're rejecting the null hypothesis. So can you talk a little bit about what those values mean in layman terms?
These values, yeah. These.
So yeah, like the difference between the t values, I think between those two would be really helpful.
Okay, let's say that, okay, let's go back to that one. Okay, let's say that let's say these
Well,
values.
actually, I should ask, when I'm running this and I want to know, like, are these values equal to each other? Which should I look at? Because I think I was looking at the PR is greater than F statistic.
Yeah, this is where the problem is. Yeah, you are right. But the thing is that that's why I was going through this without the theory up to some, this is not theory. We were talking about the formula.
Yeah, I know. Yes, I agree. We were
Yeah,
talking.
but little bit base, because otherwise we don't know what's going on behind that. And this number, let's say, in order to get the physical interpretation, mean means what? How do we explain? Mean means average. We're going to explain to the layman and say, hey, this is the mean. He might be thinking, what's the mean is? But it should be supported by something to that support. Then they might gonna think, okay, this means that you're gonna add all the numbers and divided by that one would be my mean. You need that kind of that background. So same passion. Sorry, let's go to this one here or anywhere. Okay, let's say that this is the test. Okay, this is the difference between the means now. Okay, but when it's come to the standard error, this one you cannot explain easily without having that formula in your hand. You see, how could you gonna explain to them and say this is the, I can explain you like this way. Okay, it's everything related to the distribution spread. Which distributions? Okay, I'm gonna draw the distribution here. Okay, this everything, this one, this all these are the thing is that in statistics all are randomized. This discussion, that's why we have to build up that. We were nicely built up this discussion from 601, 600, 605. We nicely built up this discussion.
This stuff makes perfect sense. I understood when you were going over this. I just want to make sure I'm understanding the pooled and this.
Yeah, pool one. No. Pool one, come to that one. I'm going to add something here. Before you come to the pool one, no setup. Okay. You have to do another test. See, this is the test for the equality of variance. You see, this test has to be done. That means that's what I'm trying to get in over there once I'm done with this one, because I'm going one by one here. And after that one, we're going to come back to here. It's like a link. You cannot do this testing. This everything, okay, this everything, these are just, I give the formula only. We don't do calculation. We don't plug in anything. You can plug in and then see that how it works. We don't have to. Okay. So what I'm trying to say that we based on these two, but now you have a situation or which one I'm going to pick here. To do that one, I'm going to add another test here. Okay. H naught sigma F equal to sigma A. That means you're going to say then, if you get a distribution of the front wheel that driven cars mileage, and then its distributions that the spread, okay, you can explain to them like this, see, that spread, see, this distribution You have a distribution, this spread. They think the same, and it should be tested. This is for all wheel. This is for front wheel. They all can be drawn into a distribution. Versus this guy, sigma f not equal to this one should be tested. See, in order to test this one, what do you need? You need the f. You need the f test. F statistic is how could you gonna get that one? Max of, sorry, I think, max of S1 F squared, S2 squared, SA squared. Out of these two, you get the max, and divided by the mean of those two. You have a two variances. Out of those two variances, you pick the max one and put on the top, and min one put on that one. That's how you get this F value. See, F value come like that. In a simply, what I'm trying to say, out of these two standard deviations, you got the finite, this one, see, this one divided by this, square and divided by square, because you have to square. 25 divided by 25, 25 here, almost like a 4, 6, no? See? 5, so 6, 36, 36. 36 divided by, see, max of this one. You get this one and divided by this one, you should get this one, almost like this one. See, with the numbers, you're gonna come to the closer that same value. Okay, so that's how you're gonna get that one. Now with that one, I'm gonna draw this the f distribution and get its f, and then I'm gonna go to f naught value and then find this p value. See, p value again what? P value is nothing but probability f value greater than f naught. Your f naught already there. F naught is this one. This is your f naught. So this p value, now again say you're gonna reject this one. See, p value is less. You reject means that which one you
this particular p-value is really the p-value of, that's really the standard deviation of the f statistic, right? It's saying that the f statistic is this far away from the actual, from like the mean of all of the possible, of the, like what we think the f statistic should be.
Yeah, f statistics is doing whether f statistics is based on, in order to run this test, you need the f statistics. In order to run this test, you need t statistics. Okay, so t test.
Yeah, I understand that they're all linked together. I'm trying to understand, like in total, like if I had to just say the f statistic represents x, I just want to make sure I'm understanding like what that sentence.
Oh, okay, yeah. The thing is that if statistics means that that's the kind of some kind of a test variable we're gonna utilize in order to run this test. You cannot run the test. You need some kind of a support, some kind of a tool. That tool is called the f statistics. How they built up this one, taking the maximum of this one divided by minimum of this one. They think this one is distributed according to f distribution. It's a standard distribution. That means actually this is what actually they're gonna do. This one we talk about in broadly in 605. See, you're gonna pick a like a, you're gonna get the bootstrap and then pick f value, f1. You're gonna get another sample, f2. See, I'm gonna say bootstrap.
Yeah, this makes sense.
Yeah, bootstrap sample. Yeah, sample one. Okay,
we're making a lot of samples.
Exactly, lot of sample. Okay, then I'm gonna do this 1,000 times. Okay. Then I'm gonna draw this one, okay, distribution histogram for that guy, okay. Distribution histogram, if I draw the histogram for this one, it looks like this, right skew. That's the distribution we're gonna utilize.
Got it.
Yeah, that's how the distribution come into the picture. But on the other hand, theoretically, practitioners have developed something called F distribution as well. That's theoretical one. This is a bootstrap, you get this shape only. But that one and the other one, they pretty much the same kind of a thing. We're going to say this is an estimate for the theoretical one. So based on that one, based on this F test, because it fits only onto the F. Why this fit into the F is the more theoretical. I don't go there because we don't do the theoretical part. I can derive that one, but we don't do the derivation. We simply say this divided by that would be definitely become a F distribution for certain reason. Because the reason is that this is chi-squared. There's another distribution called the chi-squared. Chi-squared divided by chi-squared called the F distribution. That's the reason. That means your S all the time, S all the time distributed according to this one. They were related. You go to N, you say the front wheel, subtract one. Okay, you're gonna go to its standard deviation square, and you're gonna get its population standard deviation. That would be distributed according to chi-squared of NF minus 1. Then you go to the NA minus 1. See, SA squared, sigma, see, A squared, see, chi-squared, NA minus 1. Then if you divide these two by chi-squared, mathematically we can prove that it's going to be F distribution. That's how the F distribution is derived. It's a long story. I just make it like a short because so that's how you get this distribution. So you're going to use the F statistics to make a decision. You go to the F naught. F naught is nothing but already over here. We don't do any kind of any calculation. We don't do. We're looking into their p-value. P-value is less than, is extremely small. Therefore, we're going to reject what H naught and say the variances are not equal. Then you go to the unequal one. See, unequal one, and then use the p-value for that one to make a decision about the mean. Now, based on this one, you make the decision. Once you make the decision, see, we have to go back to, I'm sorry, here. See, this one. And again, you're going to use Satat weight or pool one is determined by that test, this test. Then you say that the p-value is so small for this test, for the equality of variances, that's small. Therefore, I'm going to reject H naught. H naught means like they were not equal variances, they were unequal variances. Now you go to its p-value, Satat weight p-value. Based on that one, you're going to say, I'm going to reject this guy. The means are not the same as you reject that one. You reject this guy based on that one. Based on that one, you reject that one.
So then will you ever see, like if you go back to the SAS?
Okay, I'm gonna go back to SAS. Okay.
Would you ever see that value be the PR greater than F to be, if you saw that value, would we ever see the unequal value PR?
Oh yeah, they come. Yeah, sometimes they come. Yeah, this is because based on this given data, this test is significant. Significant means you are trying to reject the H naught, significant test. So if you're going to explain this one in the context of that regular audience, so you have to elaboratively say that one. Elaboratively say that, okay, in order to run this test, how could we run? And then see whether these engines, that front wheel driven cars mileage gonna be same as that average mileage gonna be same as that of that all-wheel driven cars. If that's the case, how could we gonna check and see? Then they might gonna say that why you're not gonna go to the averages and then compare and then make the decision. See, they might gonna suggest you something. See, they say check this one. See, front wheel and mean average already over there. Then you're gonna say then no, we cannot use this one. By looking at this one, it seems like a front wheel lab far better. You cannot decide that this is the best one. It seems like when you take the two classes, and in one class you have like 80, in another class you have like say 90. Then by looking at the 90 and 80, we cannot make a decision because you have to come to the common ground called the Z score. You have to get the Z score. That means you need that average and standard deviation of both classes. And then you have to convert that to C-square, and then you're going to compare. That kind of a thing we are doing nowadays. By simply looking at this one, we cannot say about the whole population, all the cars. You cannot make inferences about make a decision about all the front wheel driven cars gonna have the higher mileage than this one. No, it cannot be, because it's not scientific. Because of that one, we're gonna add the test. In order to run the test, you need the p-value. In order to run the test, you have to come all the way to here. See? In order to run the test, so statistically we run the test based on that the formulas that I show you over here, but you don't have to worry about the formula any of these. By simply go to this one and read. But if anybody asks what are these, you should have like a background to support something to back up. This is the backup. You go to the backup and say, hey, this is the formula for you. Go ahead and plug in and see whether it's going to get this value or not. See? So by looking at this one, but in order to come to this table, not this table for the parameter estimator, we done this one. We did the confidence interval for, see, this confidence interval for mean as well. See, the average confidence interval, we can write this one too if you want that one too. But mainly that for the test, we have two types, rule 1 or setup rate. That will be determined by this guy. Then we jump into setup rate and we are looking at the p-value. P-value means nothing but how extreme, how many data values you're gonna get, how many the differences, how many of these differences you're gonna get more than this one. That means this is nothing but this one. This is same thing like I'm gonna draw the histogram for what? X bar F minus X bar A. They are randomized too. See? They are randomized too. That's the problem. They are randomized too. So see, their mean, see, they say that the mean of X bar F minus X bar A is same as the mu F minus mu A. Now you have this come to this one. See? Now since this is not available, you're gonna go to X bar F minus X bar A. But this X bar F and X bar A is special one because it's based on your observed value. Because of that one, I prefer to put O is 0 here. See, based on observed value. In a similar fashion, you need the spread, standard deviation of the spread, X bar F minus X bar, that distribution's standard deviation. It is given by two ways. This is nothing but the standard error of X bar F minus X bar A. That's the same thing that I was talking about here. It has two branches here. See? Two ways you can get this done based on their sample. See? Sample standard deviation. Everybody's sample standard, because this is going to be definitely related to the population one. The population one not available. Then you can put the based on the observed value. This everything based on observed sample. Observed sample. You have observed one sample. One observed sample. That one observed sample utilized to calculate the data. Otherwise, you might be thinking this gonna be again that random. Yes, that's the heavy part of the statistics. Very that's why confusing, because then when you estimate something, estimate become again randomized. That's why it's become nested. That's why we stop at this stage and say, hey, no, standard error of a sample means the difference of the sample means standard error is the nothing but the sample deviation of that one. The standard deviation of that one. Now you might be thinking, which standard deviation? Sample standard deviation, because it's based on samples. All this based on sample. So when you're gonna write, you can write and then explain to them and say, hey, in order to check this, the mileage differences, I cannot just simply looking into the averages. Okay, it's not fair because it's based on the sample only. I'm trying to make the inferences about the total population. I'm gonna spread this to the all wheel driven that cars and all front wheel driven cars. if I'm going to extend that my idea to that one, this is not enough. It's not enough. This is not enough. By looking at these two, we make the inferences. These are like a very that's a primitive stage. We did that. That's why we decided to. But when time goes on, people added more scientific that flavor to that one. That's what we call the t-test, or in this case, we can say that this this t-test. T-test. We added that t-test, and then we based on this one, we got that how much chance that we have these differences gonna be extreme than this value, extreme than this value. That's what is called. So that's what we were talking about. Sorry, extreme than that one. This is related to F1, but in a similar fashion that I can say that for the this one, if you go to this one, F minus X bar A, that distribution I say like that. Okay, my convenience. Okay, this is you have this one. You have what? Observed value. See, you have observed value over here. See, T observed, T naught you have. So this area, the probability T greater than T naught, and probability of this side is a two-tail. Probability T less than minus T naught. They both come together called the p-value. P-value is nothing but probability T greater than T naught plus probability T less than T negative T naught, and this is same as 2 times probability T greater than T naught. That's the same thing. They do that calculation. We don't do that. That's for that distribution. See? That distribution for that guy. Everything has a distribution. See? But this one for F has a distribution too. F is a ratio. F has a distribution. See? This one coming from the ratio between the max of that value divided min of that one. So now you decide that one. You come to this one. Then you're gonna find the confidence interval. See, confidence interval, if you want, you can find the confidence interval, same thing. How do you find the confidence interval for these differences? Now, as I mentioned, they say that this one, see, look at this one. They say that I'm not interested in only mean only, give me a range. I'm not interested in the standard deviation. See, this one, see, give me a range. See, this is a standard deviation confidence interval. This is a standard deviation. Everything been given. Standard deviation, even that if you ask for the standard deviation, they say no. I need that the range. How that happened, that one. See, so that if you need that confidence interval for that mu of front wheel, see, it's nothing but y bar of front wheel plus or minus, so 1 minus alpha, okay, or 95%. Most standard one is 95% plus or minus. You can say TC again, critical value. You know how to get it. They do that one. The standard error of y by f. Standard error of y by f, nothing but s of this one divided by the square root of n f. Is that one? In a similar fashion, you can say confidence interval for, you need this one, a confidence interval for mu f. The similar fashion, you can go to the mu. I'm going to say sigma f, standard deviation, confidence interval. It's going to be what? It's going to be that chi square divided by, see, sorry, this one, n, I think n a n f minus 1, n f minus 1 s sf squared over chi square. Chi square. That one is chi square. That's how they got that one. Comma, this one. Again, nf minus 1 sf squared over chi squared. This one called the lower bar, this one called the upper. That's why you have a 2. So everything has a formula behind that one. See, later on they say they give me this one. See, whole one. Now they have a difference here. Now we can write the confidence interval for that guy. See, pool one and the setup. But in order to write the pool one, if I write the difference now, I need the difference. Confidence interval for the difference. See? Confidence interval for difference. See? Confidence interval for mu f minus mu a. How do you write that one? Y bar f minus y bar a plus O minus TC. Okay. And then to get the standard error of y bar minus y bar a. We have y bar a. This one we already discussed here. See? That's the one I discussed earlier. Okay. It's already there. They do the calculation. You don't have to worry about that one. They do the calculation.
Hey, Professor.
Uh-huh.
So without looking at the formulas, I was a little confused on how to interpret the data in order to reject or accept the null hypothesis. So I know that we're looking at p-value, whether or not this model is significant. That's one of the factors that we have to take in. What about how do we interpret like the f value again? Versus then we move up to the equal unequal methods of the pooled and Satterthwaite.
Yeah, Satterthwaite. Yeah, that's what I say, that you check see, you check the equality. You have to run that test first. You run in a test over here. See, that's why I'm writing over here very clearly. See, you run this test first. Okay, this is the first step. You run this test first. You want to check this one, whether they were equal or not.
We have to do that manually, is what you're saying? Or
no, we have to run this one and see whether you have equal variances or not. Do you have equal variance or not? How could we know? We don't know. See, that's why we do this one. That's why I was telling you, do this one first.
Right. So how do we interpret that to accept or reject?
That's why we say that we have to say that you're going to interpret means like that. You're going to say that, okay, did you check the equality of this? See, look at it. What this means like this is the, what is this one? This is the variance of the thing, variance of what? Front wheel driven cars, mileage.
Yeah.
See, because I don't, because when I write in the like a heavy, that plain English is going to be very lengthy, plus that it takes time consuming. But you can interpret like that way. Okay, you know what this represent. What this represent? This represent the mileage, MPG mileage, the MPG city or MPG highway, whatever that you get, we simply call the mileage. The mileage, okay, the variance of the mileage for the front wheel driven cars. This one is that the variance of the mileage of the all wheel driven cars. Are they the same? You're going to check whether they are the same or not.
Right.
In order to do that one, you use p-value. Simply use p-value. Forget about that. This formula. You simply go to p-value. Okay, that's it. You set that up. You have to set up this this one. You have to set this up, or you have to write in plain English. Write in plain English. Write in plain English. That's why that this you know that data analytics is a part of statistics. It's a part of that symbols too. We cannot disregard and go and then try to explain to the audience. You cannot do a better job because the audience not going to be happy. Audience are sometimes, we have like a very the capable people who really want to get an explanation through that one. That's why you have to have sometimes rigorously both ways. You write in plain English, get a rough idea about what's going on behind that one. How could I'm going to write this one in a shortcut? You need the shortcuts. Very easy. Variance versus variance. That's it. Variance not equals to variance. Simply, you can write like that. See? How could you this one? You don't need this formula. You don't have to write the formula. I'm writing for you to have a look at it. You don't write it back to me. No, don't do that one. You simply go to the p-value and say, hey, this is my test. Okay. This is simply you're gonna write like this. I'll show you. Okay. Simply you're gonna write like this way. Okay. You're gonna write. Okay. First step. Okay. Step one. You're gonna write like this way. Okay. You're gonna say that H naught. Okay. At least you cannot just put the null hypothesis and in plain English. It's too much then. Okay. You're gonna say the variance of mileage of variance of mileage of front wheel driven cars equals to is equal to that of the all-wheel driven cars. You can write like that. Okay, driven car. That's it. You write this one. You're gonna check that they are variances. Where are the variance coming from? Coming from the distribution. They are distributions. That difference I show you over here. See? The variance means this variance. Here, see? This variance. That variance. This gap. This gap. See? Are the same. Okay. Versus its natural counterpart. Anybody when we put like that, they know that what we're talking about. Counterpart. Then we're gonna say since p-value is extremely small, we infer. You don't have to say rejected now. We can come to say we infer that they both don't have the same variances. That's it.
I got you. Okay.
Like that. And then like
Yeah.
that, yeah, you don't have to go to the notation because but in the textbook they have a notation because I cannot skip and go. Because it's a part of this course. That's why this
No, that makes sense. I
Yeah.
get it. Yep.
Yeah, like that. But when you write, you can write any way you want. Write plain English, anything, any way you want. But on my side, that because on my side, you don't have to throw everything that I'm just giving this one for you to get a clear idea. Then you go to the second step. Let's go to the second step. Now you go and say, therefore, you can say, therefore, we have to use the setup weight method. Okay, like that. Then you can say, therefore, we have to use the setup weight procedure method to check whether the mileage, average mileage for both type of the same. That's it. You write that one. No, that means if you want, you can say that is. If you want, you can say that is H naught mu f equals mu v for your own convenience. If you want.
So we would look at the p-value to determine.
Yeah, again, then now you go to the
infer-
setup rate. Yeah, exactly. Now you go to the setup rate and look for the p-value. And since p-value in setup rate, see, I'm gonna go here.
Yeah. So if p-value is less than is
Extremely
significant,
small,
then we can
get H
say we can infer that it's the variances are not equal.
naught.
And so that means we look at the Satterwith method to determine kind of test.
that one exactly.
Oh, I see. Okay.
Yeah, you need this one to set up weight method. That's why that's the proper the use of that one. You do this one based on that one. You go to set up weight method to say that p-value is extremely small. Therefore, you say their mileage are not the same. do different types of that. You can infer that one. You can infer and say that that for all that cars produced in a certain factory, or cars produced in a certain region, or in the USA, or in North America, or in that whole American continent, are not the mileage not going to be the same based on that given that theoretical aspect and based on that data set. That's most of the time we're going to come up with that it's been more scientific based on, because that we're not going to simply looking into the averages. The average been incorporated into some other formula and then come for that conclusion. So that's the way you have to do for all these three. All these three you can do like that. All the other cases, even you're going to run this one, you're going to go ahead and run part B, same thing. Now this time you're going to go to the wagon and say that their mileage, you're going to check. Then you're going to check that their mileage about the MSRP or that invoice in that USA or Europe, which car is the most expensive. See? Like that. You can check that one. The similar way that you run that one and then build up that kind of a discussion. You can write that in any way you want. See, any way you want. See? Like that.
Yeah, that makes sense.
That's
Thank you.
So yeah, that's the step 2 here. So then that if you go to this one, look at that. They were looking for that part. Sorry. Part. They were looking for. Oh, why we gonna run this one? Then we're gonna go to part 3. Say univariate. I'm run univariate. See, let's run univariate. See, MPG variable is MPG city. They were asking about something from us. What they were asking about? The average, no? They asked about the average of that MPG city. Question number 3, if I can remember. Okay, let me get that one. Okay, go to this one, go to assignment, go to homework 1. Okay, these 3 tests, okay. Okay, mean mileage for all vehicles. The other one is MSRP variance for the vehicle from USA. Mean mileage for all vehicles. But you have to find out what? Estimate and the standard error. Estimate of mean mileage for all vehicles. So let's see that whether we have taken into account the all vehicles here. Do you get the all vehicles? Yes. See, all vehicles. I don't go particularly say anything because this is for all vehicles. So I run this univariate for all vehicles to get the. Sorry, I didn't. Oh, I got that one. That's okay. I'm gonna run this one, and then if you get the univariate, that will give you the descriptive statistics. Then they're gonna ask us to find this one. They ask, okay. They ask estimate. Where's the estimate of the sample mean mileage? See this one. Then they're gonna ask standard error of the mean mileage. That's this one. Okay. Standard error. That means assuming that your estimate gonna be distributed according to certain distribution. That means you can draw the histogram for this one, this guy, but this is based on your own value. That means that you have X bar value. See, sorry, you have a Y bar value, 20.06. You have a Y bar value for all 20.06. That 20.06. Yeah, 20.06. Okay. Then you have a standard deviation. See, standard deviation for all 2. I'm gonna write this one first and then show you 5.224. Now they're gonna ask about that standard error of y bar all, which is y bar sample this one is all divided by square root of n all. N all is how much? 428. Okay, I'm gonna show. Okay, and 5.24. That's how they got the 0.25. Okay, this is what I'm gonna write out. This being given, this being given. This is this divided by that will give you this. It's nothing but if you want to explain to somebody, say what this means, the standard error. What do you mean by standard error? You have a standard deviation. Why standard error? Then you have to say no. Y bar all not gonna be only one. It is so many of them. You can get them by bootstrapping, and then you can draw the histogram. You can get the smooth curve, and you can go to the mean. See, mean of y bar all same as mu of all. Since you don't have a mean, you go to the y bar all, what? The observed one, which is 20.06. Then you go to the spread. Standard deviation of y bar all is nothing but standard deviation of all divided by n of all, which is 0.25. That's the spread. That's the spread. Whatever the sample that's a spread. Actually, this one is this one. It's d of y bar all is like this. Sigma of all divided by square root of n all. Since you don't have that one, you go to this one and you calculate. Those are estimate. Now you might be thinking this can be estimate. Since this is an estimate, can this be drawn as a histogram too? Yes, as I said that we stop at this stage because we cannot keep going. We cannot keep going. We have observed sample. Based on the sample, we make the inferences. Everything distributed. So they were looking for the sample standard deviation. That standard deviation. The same way that they were looking for the second part, they say that, okay, MSRP, variance for vehicle from USA. Okay? Standard error. Okay? So you do the same thing. Now this time you will say origin is USA vehicle. The MSRP, that average would be how much? Variance, sorry. This time they were looking for the MSRP 1000, sorry. Oh, no, numeric, this one, right? 1000. Okay, now they were looking for the variance. Okay, you go to this guy, see, variance. Now they're gonna ask about the what? Standard error of the variance. Where is the standard error? Not the standard error of mean. Standard error of variance. That means they draw this one. This is what I'm talking about. Standard error. Standard, they got this one. Standard deviation. See? Standard deviation of, see? Standard error of variance. This guy. See? S square of USA. See? SU. I'm gonna put the SU. That guy. I need the standard error of this variance. See? This guy is same as the standard deviation of SU square. See? If you draw the histogram for that guy, it has a mean, it has a spread. That spread is this one. How do you find that one? How do you find that one? that in order to find that one, so, you have to use this formula. One second. Standard error of mean, variance, and standard deviation estimator. This is a very heavy one, but I'm showing you this formula for the mean. Okay, mean estimator is standard error. Variance, this formula, this part. Okay, this part. If it is that standard deviation, okay, standard variance, standard deviation of variance. Okay, this one. 2 over, see, this one. Okay, I'm gonna write this one for you to see clearly. It's nothing but, okay, and the deviation of this one is, okay, nothing but standard deviation of u, observed one, times square root 2 over nu minus 1. Nu minus 1. Then SU. SU. Do we have SU? You need that calculation you have to do by hand. SU. Yes. See? 11.71. 11.71. 11.71. 2 over NU. How many USA cars we have? 147. 147 minus 1. Use that formula. You have to be careful. It's coming from this one. It's not the standard error of me. They were looking for the standard error of the variance. Keep in mind that what they were looking for. Standard, that means the standard deviation of the variance. Sample variance. It is nothing but the observed standard deviation times the square root 2 over sample size minus 1. Like that. Because I saw that when I was teaching that they were making a mistake because they haven't gone through the theory, not the theory, that at least the rough, that idea of what's going on. These are not theory. Keep in your head. Theory very rigorous. You haven't seen theory, you might gonna run away. Very extremely heavy. So we don't do data analytics, the theories. We do the only programming. Programming part is the part of the computation. But we need to have like a rough idea what's going on. Okay. So then that one, see, that's how you're gonna answer that, those two. Number 4, I think we pretty much explained that one. And then this one, MPGCT, then you're gonna say that, okay, now they add to multivariate. See, this one, same thing that we were talking about earlier. I think we did that one. Now, instead of that same thing that been explained by the engine size, wheelbase, and horsepower, that means you're gonna get a what? The plane. You're gonna get the plane. Look at what's gonna happen. Okay. You have that. If I use these three, if I'm gonna draw this one, see. Then I have MPGCT. I'll show you. Okay, give me 1 second. Okay, then this side I'm gonna put engine size. Another side I'm gonna put wheelbase. Then this one I'm gonna put horsepower. Horsepower. I'm gonna call engine X1, this one X2, this one X3, this one Y. I'm gonna show you. MPGCT. This X1, X2, X3. Okay, right there. So your model would be what? Y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. Or when it comes to the sample one, sorry, this one, sample one, b naught plus b1 x1 plus b2 x2 plus b3 x3 plus 2. Then you have a plane. Okay, you have a plane, fitted plane. So that one they say to their explain. And then when you run this one, you can see something, okay, very clearly. Oh no, no, I don't need that. I'm gonna run this one and then try to elaborate. What's behind this? In order to run that one, you definitely have to use the see, you use the reg over here. See, then you get this one. See? You can see what this means, what they are trying to do over here. See, how could you gonna interpret this one? You say you can interpret this one. See, everybody has a 1 degree of freedom. Look at their estimate. Look at their standard error. We know how to get the standard error for each and every one. See, do we know the same formulas for this one? When we have a the 1x, we know up to here. But when we expand it, we have other formulas too. See, then you know how to get the t-value means this divided by that. Estimate divided by the standard error give you a p-value, absurd t-value. And probability more than this one give you p-value. If you want to see that whether this is plain, the engine size is, whether engine size gonna be important in explaining the y variable, which is the MPG-CT or not. Whether MPG-CT engine size is important in explaining the variation of the MPG-CT means you're gonna run the test for that. Or even wheelbase. In every test can be say whether wheelbase is see. Separately, you can say only wheelbase gonna be that. See, these are for the individual test. Wheelbase is important, significant in explaining the variation in the MPG-CT or the horsepower. Everything you can check that. See? Sometimes see, so this is almost like everything here rejected. That means they were that you can check this one. See, important. See, not zero, not zero, not zero. Important, important, important. Explaining the my MPG-CT. Or you go to this one and overall test. You run the overall test. What that means? You go there. Okay, you're gonna run individual test. See, you're gonna run this one. Say H naught, beta naught equals 0 versus HA, beta naught not equals 0. H naught, beta 1 equals, sorry, equals 0 versus HA, beta 1 not equals 0. H naught, beta 2 equals 0 versus HA, beta 2 not equals 0. H3, H naught, beta 3 equals 0 versus its counterpart HA, beta 3 not equals 0. You done. Okay. These are for the individual testing. Individual testing for each variable using t-test. T-test or t-statistic. The other one is you can overall and say, see, H naught, I'm gonna say B1 equals to B2 equals to B3 equals to B4. I'm sorry, B3, no, we have only B3 up to. It's not B3, I think. B0, B1, B3, yeah, sorry. So overall check whether they are the same. See, they are the same, and together they all equal to 0. See, 0 versus its counterpart. We're not gonna write with the counterpart HA. We're gonna write at least one of them not equal to 0. That is beta I not equal to 0. At least, see, I maybe goes from 1, 2, and 3. At least one of them. At least one day I know for 0. That's how you're gonna write it. You cannot say that which one. We don't know. We don't know. We don't know. This one called the overall test. Use in what? If using overall test or individual testing for overall test for using if distribution or if statistic. That one we can check. Then overall that by looking at this one, if you go to this one, see, you reject H0. Reject H0 means there would be at least one of them, one of the variable, at least. We don't know which one. We don't know. That's why we have to go to multiple comparison. That's a different discussion. We have to go to multiple comparison and see which one's going to be important in explaining the variation of the MPGCT. See, but here you can individually looking into this one and make the decision as well. Here overall test. Overall test. This one is R statistics again, that ANOVA table. You have ANOVA table. Based on that one, you know how to read this one. Like that. Here that overall test. That's you're gonna just at least one of them not equal to 0. We don't know which one. We don't know which one. This one beta 3. See? These three. Beta not, we're not gonna consider too much because that's okay. It's okay. We get the important ones only. If you have this a multiple regression. It's called multiple because there are many variables over there. So this is the same discussion we extend. Okay, you guys write whatever that you flexible of writing, explain any way that you like. Okay, and then if you need any help, just email me. Then if you need any one-on-one, then any help when even the weekends, anything. Okay, before you're gonna finish, you wanna do a good job and you feel like, okay, I wanna write up this one in very nicely, but feel like I get stuck and then I don't know how to interpret this these notations and everything, or this concept. Just let me know that we can one day, Saturday, Sunday, with any day that it, even tomorrow, doesn't matter. Then you just let me know, then we can go through these ones again and again. But we're gonna go through this one, and then as I said earlier, don't worry about this turning this one this Sunday. I have given you that flexible time for you to turn in anytime you want within this term. And then if you wanna wait until that Monday or to go through this one, because this discussion we're gonna extend, same discussion. This is the regression discussion we extend. These are not important that much. These are we can neglect and we jump into the regression, keep going on the regression. So so do you guys have any more questions that I like to go through? Anything that you wanna get clarified? Anything before we gonna go? Otherwise, we are planning to wind up over here. Anything?
I think I'm okay.
You okay?
Good as
Yeah,
well.
you okay too, Angela?
Yes, I'm good as well. Thank you.
Yeah, then write it down. Write it down any way that you want. That mainly that when you're gonna look at. Okay, I'll show you that how we have that one. Okay, I'm gonna show you that little bit before we. I showed that one too one time. Say week 1. Okay. What is this one? Is that the one? Oh, what is? Oh no, this is a Python one. I think somebody did the Python. You say no. Okay. Okay, this one. Okay. Let's a little bit have a look at it. Okay. Okay, this is it. Okay. Very good. If you want, you can put the question here. Okay, go to part A. Okay. So then you just explain what you're gonna do. See, by transforming an MSRP and invoice variable from a string to numeric value, if you want. See, if you have that kind of a habit to do like that, that's gonna be very useful. See? And to this one, SAS was able to generate scatter plot matrix using the information continuous variable. The following is the code for such procedure. All the way up to here. Data, see, the variable transformation data for MSRP and invoice is transformed into thousands since their corresponding value in the data set is relatively large. Okay. So then we're gonna go over here. See, we talk about this one. Okay, in general, scatter plot display a correlation between a pair of variables. In addition, there are the number of scatter plots. This factorial I showed the other day how we got the 10. Okay, any given set composed of n variables. The scatter plot matrix is an organization of pairwise correlation in one single graph. The scatter plot matrix in figure 1 shows the correlation between, and now you're going to talk about MSRP versus invoice, this guy, variable by matrix. And the data set that pertains to the car brand. Should be noted that the comparison between the two paired variables, this and this, upper left and then this one, MPGCT. So almost perfectly correlated since their corresponding values in the data set are relatively close to each other. You know, they see that observation you can mention because this is the same thing. Invoice and MSRP mean pretty much the same thing. It's a manufacturer suggested retail price. This is the one that they have sold the car invoice. Say that the car has sold to that they're gonna go with a pretty close value. That's why they were very highly correlated. That one you can mention. See? Whatever you observe. See? On the other hand, rough inferences between the pairwise variables are as follows. See? And invoice this one 2 horsepower. The more expensive car is, the more horsepower it has. 1000 and invoice to MPGCT and this one. The more expensive car is, the more it consumes fuel and the less mileage it covers. Horsepower to MPGCT and MPG highways. The more horsepower car has, the more it consumes fuel and less mileage it covers, like that. You can compare, contrast. That kind of a discussion you can build. For the t-test, you can write in plain English. See? There's no difference in mileage between front wheel and this. There's no difference. There's no difference in mileage between the front wheel and all-wheel driven car. There is a difference between this one. And these are the generated code. And based on the t-test result, using the data from this one, all observation has mean of this one, while the blah, blah, blah. Then you're gonna write down the results indicate that there's a statistically significant difference between the mean mileage for all-wheel and the front-wheel driven car, because having a t-value this one with t-value this one, if you want that, you can indicate both. They go together. Conclusion: reject null hypothesis. And then what is your inference? What you're gonna make the inference? That means there is a difference in mileage between that inference. Then you can conclude that one, and you can write that your decision. This is a conclusion. Then the decision in the context of the given problem. Conclusion would be there's a difference in mileage between the front wheel and all-wheel driven cars. So the similar format you can use for all these three. Okay. So here that when it comes to that talk about the setup rate, see, those one you don't have to that very particularly, you don't have to mention if you're on the right track. If you have picked the right method, you just stick to go. And then I think here that say using the setup rate method too, that one little bit mentioned that you don't have to say about this one. We just, I was showing you how to that make the come to that right table, sorry, the right row from this table using this one, but you don't have to that deliver them back to me and say, hey, that we first use the equality of variances like that, the way that I was telling over here, that first step, that's the step that you should take, not the right. Okay, if you want, you can write too. If you want, you can write too. But simply, if you go to that one and say, they have simply, you have taken based on the t-test results using the data from MPG, all vehicle and all this one. And these results indicate there's a statistical difference between the mean mileage and this one based on the setup. You can say the based on the results, not the results, are based on the setup rate method or the pool method. You can say whether you're gonna say statistically significant or not. Instead of this one, the results indicate, you can say based on that method. So you don't have to that say that method, the step 1 and step 2 like that. I was showing you that this is a step that you have to take and in order to make the conclusion, but you don't have to write it down. You have already picked the right method. When you say based on the pool method, based on the setup, it's more than enough, because you already know based on the other test that you have picked the right method. But if you don't mention anything, I think this should, here we have to mention that one here. So based on setup method in that particular case. And then go to B, same thing. You do the same thing, and then you can discuss based on the result rather than based on that whatever the method, pool method, based on that one, the results indicate. Okay, based on that one. So that will cover whether you have already run that test for equality. That one. Then we already discussed about this one. Okay. Then the see, why we read this one. And based on the results computed and generated by SAS figure for issue overall analysis variance. See, number of see. So you can talk about that overall test. Overall test. See, indicating that the model account for significant amount of the variation for predicting the gas mileage with the car's engine size. See, that for the by looking at the ANOVA table, you can make the difference decision. See. For A, okay, for A, by looking at this one, you can make that where the engine size will account for the MPGCT, engine size. By looking at the F value and P value together, you can say that the model accounts for a significant amount of variation for predicting the gas mileage with the car's engine. Gas mileage by a car's engine, not with a car's engine. We don't have to worry about the plots. Okay, plots we're going to talk about later. The same way here we can say by looking at indicating that the model accounts for the significant amount of variation for predicting the gas mileage with the car's engine size, wheel base, and horsepower. Counts. We reject it now. They're not gonna be they're not gonna be at least you have to indicate in the model accounts for significant amount of variation for predicting the gas mileage with a car, at least one of these, at least by car's engine, wheel, horsepower, one of these, at least by one of these. Okay, it's not gonna be necessarily be all, at least one of them not gonna be 0. That one of them, but all can be not 0 too. So that kind of writing up you can do, and then put the code here. Then you don't have to put this the graph. Okay. Graph we don't. I need this table. I need this guy. I need that little bit explanation. That's it. Write anyway that you feel like they're comfortable to you. Okay. So as I said earlier, that if you get stuck with something, just let me know, and then we continue the same discussion, and then we move on to that next 3 chapters. There's again the regression. These all the properties we talk about that one, and then we continue this discussion. Okay. So I'm gonna wind up over here since you guys don't have any questions, and then you guys have a good night, and then have a nice weekend. Stay safe and be well. Okay. See you guys next week.
Thank you. Goodbye.
Thank you. Bye bye. Take care. Good night. Okay. See you next week.